Hi everybody, today we're going to talk about partial pressure and perhaps do, if we have time, collecting a gas over water, which we'll actually do a lab on as well. And you've kind of done that as well. You displaced water and collected hydrogen gas, and we lit it on fire in a lab. We did that one already for the last unit. So today we're going to talk about partial pressure and mixing gases. And what you'll notice about gases when they mix evenly. So they'll always form a homogeneous mixture, a solution. So if I were to show, like a container, and I were to have my two gases in it, I would have, my one gas spread out here, and then if I were to do a different gas, in a opposing color here, I would have something like this. And so I have my two gases, they spread out evenly. Now each gas, because they're not interacting with each other, remember the gases are colliding elastically, they're not attracted, they're moving in random straight line motion, they'll behave as if they're the only gas present. And so we can make a statement, we can say that the total pressure of the gas is equal to the pressures of the individual gases added together. It's really that easy. If I gave you oxygen gas in a container that had 3 atmospheres, and I gave you worth of pressure, and I gave you helium in the same container with 2 atmospheres of pressure, all you would do to find the total pressure, the P total, would be 5 atmospheres. So it's really that easy when we're talking about partial pressure with gases. Now things get a little bit more complicated though if I don't give you the pressures. What if I were to give you like the moles of each gas? So let's say I were to give you, the moles of O2 was, let's say, 8 moles, and the moles of helium was maybe 4 moles. And I ask you what's the partial pressure of each one, what's the total pressure? Well, the thing is, I'd have to give you the total pressure in order to find the partial pressures. You can't do it without that knowledge. So, for example, I could give you, I could tell you, all right, well, the P total here is equal to 24 atmospheres. And so then we could use a proportion. Well, we could look at oxygen. Oxygen, for its 8 moles, it's exerting X atmospheres of pressure. Whereas the total moles, which is 12 moles added together, we know already is occupying 24 atmospheres. So now we could do the math and we could figure out, okay, well, what's X? So 8 twelfths, that's 3/4. So what's 75% of 24? Or you could cross multiply, if you wanted to. You could do 8 times 24, and then you could divide that by 12, and you would get your answer as 16. So we would have this as 16 ATM. So we know that our oxygen is exerting 16 ATM, and we could find our helium one of two ways. We could set up another proportion for helium, or we could just subtract from 24, because remember, P total equals pressure of oxygen plus pressure of helium, and so the pressure total was 24, the pressure of oxygen is 16, the pressure of helium we don't know, that would be 8 ATM. So that's how we could do these problems. They're straightforward. We could practice some of them, but they're pretty easy to do. Okay, so let's talk about vapor pressure because it becomes really important with partial pressure. We'll come back to that. We'll sort of weave it all together. But talking about vapor pressure, when we think about what it is, we look at a gas above its liquid. And this is once the liquid has evaporated. So the idea is if we were to draw a container here and have our liquid here, and we have some of the liquid on the surface, this liquid on the surface evaporates and forms gas up here. That gas exerts pressure. That's equal to our vapor pressure. Now, as far as vapor pressure is concerned, there's really only two things that can affect it. The first thing is it tells you how warm the liquid is, because the general rule is the hotter the liquid, the more evaporates. The more that the liquid is able to evaporate, the more gas forms. The more gas forms, the higher the vapor pressure. And there's a reference table that shows you this, and I have a picture of it in the notes called Table H. And you'll see this on Table H, what it looks like. So that's the first thing. The second thing is it tells you about intermolecular forces. The stronger the intermolecular forces, that means that you have less evaporation. If you have less evaporation, that means that you have less gas. And if you have less gas, that means that you have lower vapor pressure. So stronger forces, lower vapor pressure, higher temperature, higher vapor pressure. Those are the two relationships you really need to know. Now, if we look at, not sure why that says that again for partial pressure. Let's go on to vapor pressure again and talk about that. So if we look at vapor pressure again, let me show you the chart that I wanted to show you, Table H. This is showing you how the vapor pressure is affected by the temperature. And so what we can see is that as we increase the temperature, so I have the temperature going up, and I look at the vapor pressure, which I can highlight here, the vapor pressure will increase as the temperature increases. So, if I'm at 25 degrees Celsius over here, for propanone, I'll have a vapor pressure of about 30. If I'm at 50, I will have a vapor pressure of somewhere between 80 and 90. More gas evaporates. As that gas evaporates more, that tells me that there is in fact more gas that is exerting pressure. That means that there is a higher vapor pressure. If I do it for another substance, so now we compare, let's erase these points here. So now let's say that I was going to compare propanone at 25, and I was going to compare water and see what it has the same vapor pressure. So I can see that if I want to see propanone at 25 and I want to see water, let's compare the same temperature first, different vapor pressure. What I notice is that the propanone has a higher vapor pressure at any temperature, but at 25 degrees C specifically. What that tells me is that the propanone has weaker forces. So propanone has weaker forces than water. So that's something that's interesting about vapor pressure and this graph. Now something else that we can look at with vapor pressure is boiling point. And I'd like to do that here. Let me insert a page really quick. And when I boil water, the thing that you should notice about it, if we have water here, is that when I boil it, I get bubbles. And when I ask people what's inside the bubble, they always tell me, oh, there's air in the bubble. And it turns out that that's not true. There's actually water vapor. So if this is boiling water in a container, I see the bubbles of the boiling water. Those bubbles of the boiling water are actually water vapor bubbles. And when we boil, something very special is happening. When we look at this bubble, the pressure inside the bubble is pushing out on the bubble here against the pressure outside the bubble that's pushing in. And when we boil, the pressure in the bubble is equal to the pressure outside the bubble. Now, why is that so interesting? Because the pressure in the bubble is the pressure of the vapor. It's the vapor pressure. The pressure outside the bubble is the pressure of the atmosphere. And this is what boiling is. Boiling is when the vapor pressure is equal to the atmospheric pressure. If we go back to this graph up above here, you can think of this as, instead of vapor pressure, if you think of this as atmospheric, this becomes a boiling point curve. Water, we can look at its boiling point. Water normally boils at 100 degrees Celsius when the pressure is standard. If we take water up onto a mountain and we try and boil it up there, what we'll see is that the pressure on, like Mount Everest, for example, is much lower. Let's say 50 kPa. The water will actually boil at a lower temperature. We can even get water to boil at room temperature. If I lower the pressure enough, I can get water to boil at around room temperature, and I can do that demo for you in class and show you that. Alright, one last thing I want to tell you about in this video is collecting gas over water. We've done this in a lab. We've had our reaction over here that I'm circling. We did it with zinc and hydrochloric acid. We saw the bubbles, and we piped those bubbles in through tubing into a collection tube for gas, and we collected it. Now we can actually, now that we know a little bit about gases, some of the quantitative stuff, I could tell you how much gas is inside this container. Because I know the total pressure in the container. So if I know the pressure total in the container, it'll be equal to the pressure of the gas that I collected, plus whatever pressure of water vapor has evaporated. So let's say, for example, that I collected that hydrogen gas that we lit on fire, and I know the outside pressure, which is equal to the container pressure, is about 760 torr. I can look up on a chart what the vapor pressure of water is at any temperature. So let's say I know the water vapor pressure is maybe 20 torr at that temperature. I know the pressure of my gas because the total pressure, based on partial pressure equations, will be equal to the two pressures combined. So the pressure of my gas will just be 760 minus 20. The pressure of my gas would be 740 torr. So we'll do this in a lab, and you'll subtract the vapor pressure. This calculation is very, very easy. All you're doing is subtracting the vapor pressure. Now, one more thing. This slide here was another partial pressure slide that got sort of displaced. So I had this equation here. We talked about doing the proportion down here. So we talked about this. I put this in on the other slide. I didn't know where it went, and I found it. We could also use PV equals nRT and very simply just add the pressures together from each individual calculation. But this one we don't really do very much. This one's rare, and I can do this one in class with you if you'd like. You can do an example with this where we just add all the pressures together. But this is it for this video. Again, we talked about partial pressures. Very easy, adding together the pressures or using the moles in a ratio to figure out the pressures. We talked about vapor pressure, what it means. We talked about using the graph here. We talked about boiling water and how it relates to that graph, how this becomes a boiling point curve. And we talked about collecting gas over water. Alright, thanks so much for watching, and we can discuss this in class. Have a great day.